So last time we were basically looking at the generalization of Newton's law of gravitation to the relativistic formulation, and we said that we actually do not have any guidance from equivalence principle to write down the equation, but we basically went by analogy with electromagnetism, and we said that like you have an equation satisfied by the gauge field, some derivatives acting on the gauge field is equal to some source, and the Newton's equation also is of similar kind, that the derivative of the gravitational potential, rather Laplacian of the gravitational potential, was proportional to the mass density. So we decided that we will try to use the fact that this equation has similar behavior, a similar appearance as the electromagnetism equation. We would try to generalize the expressions to relativistic formulation. And we decided that we will first look at the right-hand side of the equation, namely replace mass density by a quantity which is relativistically covariant object. And we figured out that what we need to write down there is a quantity which is called the energy momentum tensor, whose conserved charges are the energy and momentum 4 vector, and whose zeroth component is the energy, which in the rest frame would become the mass. And that is how in multiple steps you would actually arrive at the mass density expression in the Newton's law. So we derived that energy momentum tensor in the last class, and we said that the total energy momentum tensor, say for a charged particle, would involve the energy momentum tensor of the electromagnetic field plus the energy momentum tensor of the charged particle, which is of course is a covariantly conserved quantity. Okay, and we said that this essentially fixes the right-hand side of our expression of the would-be equation for gravity. The expression for T alpha beta and T alpha beta electromagnetic are given here. I've corrected the typos and now it's in correct form. So we know what is the right-hand side, namely T alpha beta total. Okay, we want to ask what is the left-hand side of the equation. And again, we go back to the non-relativistic case to get some guidance as to how we proceed to get this equation. And we know that in the non-relativistic limit, the left-hand side had a Laplacian acting on the gravitational potential phi. Okay, and the gravitational potential itself appears in the zeroth component of the metric in the following way, that G00 is -1 times -2 phi. Okay, so clearly these two facts tell you that what we should be looking for is an equation which involves second derivative of the space-time metric, because if you have that, then when you take non-relativistic limit of it, you would get a term which has second derivative of phi. Okay, so the equation that we are looking for is the equation involving two derivatives of G alpha beta. Okay, now so far we have already studied various kind of quantities generated out of the metric, and one thing that we had figured out, that if you look at the terms which involve only the first derivative of the metric, then it is not a tensorial quantity, and if you look at the second derivative of the metric, then typically it should be writable in terms of Riemann tensor or its contractions. Okay, so generically we should be really looking at the Riemann tensor. Okay, so let's consider the Riemann tensor case. Now, of course, we could have considered Riemann tensor as a left-hand side of the equation, but we know that the right-hand side of the equation contains only two indices. Okay, that is first thing. And second thing is that the right-hand side of this equation contains two indices, which are and the energy momentum tensor is symmetric under the exchange of those two indices. Okay, so therefore, what we should really be looking at on the left-hand side is a contraction of the Riemann tensor, so that you have only two indices left over, and that object has to be symmetric under the exchange of those indices. And we of course know what those quantities are. One is, of course, the Ricci tensor, which is known to be symmetric under exchange of alpha beta. And the other quantity is G alpha beta itself, which is, of course,
Sir?
symmetric under, yes.
So is the Ricci tensor the only option if we contract the Riemann tensor? I mean, they are telling me other options too, right?
No, Ricci tensor is the only option.
Actually,
There is
we
no,
add upper mu, say alpha mu beta. We in the lower part we contract that with the middle index.
yes.
If we don't contract that with the middle index, then we will get some other tensor also, and that will be also a second rank tensor.
No, no, no. See, okay, let me try to understand what you're saying. Okay, so let's kind of go back to some Riemann tensor expression. You may have to scroll back a lot, but it's okay. Uh, okay, but anyway, yeah, maybe somewhere here. It's taking a lot of time. Yeah, suppose look at this expression. Okay, tell me what is it that you want to say? This is a
Samson,
Riemann
in
tensor.
which expression we replace the sigma with mu.
Yes.
Now we could replace mu or rho with mu too, and that will
Sorry,
also give a second rank
sorry,
tensor.
sorry. Instead of contracting mu with sigma, you want to contract mu with rho.
Yeah.
Yeah, but that's the same thing because rho and sigma are antisymmetric. So contracting mu with rho is just minus of contracting mu with sigma,
Okay. Okay. Okay.
right? So you don't have any option. You cannot contract mu with nu anyway because they are already antisymmetrized. Okay,
Okay.
so there are
Okay.
only two possibilities, but those two possibilities are related by sign. Okay.
Yeah. Fine.
Fine. Okay. Okay. So here we go. So we are left with the choice, which is either you write down r alpha beta times some number. Well, not either. You write down r alpha beta with some number plus some other number times g alpha beta times r. Okay. Now, of course, you could have said I could just write down just g alpha beta and not r. Okay. Well, you could have done that also, but um, uh, but we know that the left-hand side of the Newton's equation should necessarily involve two derivatives of the metric. Okay, so if you write down b times g alpha beta, it satisfies the condition that the left-hand side should be a symmetric tensor, but it does not satisfy the condition that the left-hand side should contain second derivative of the gravitational potential. Okay, otherwise nothing stops you from writing a term, say c times just g alpha beta. Okay, in fact, at some other point we will do that, but right now let's not get into it. Okay. So this is a kind of expression that we could write down, and we of course need to determine what a and b are. Okay, so both these numbers need to be determined. Okay, so okay, so yeah, there's a typo here. We will now use the fact that yeah, maybe I will not. So we now use the fact that the energy momentum tensor is covariantly constant, and we can use that to determine uh, b in terms of a. Remember that, like, if you want to use the condition that energy momentum tensor is covariantly constant, which is this equation, that imposes only one condition. Okay, namely you take the covariant derivative of the left hand side and set it equal to 0. Okay, now that cannot determine both a and b. Okay, so all you can do is to eliminate one variable in terms of the other. Which one you eliminate is up to you. So I just said we'll eliminate b in terms of a. Okay, now uh, when you take a covariant derivative on both sides, right hand side is 0 by just the conservation that we studied in the last class. Left hand side is the quantity that we have to impose uh, because the conservation of energy momentum tensor demands this. Okay. Now, what we really want is that this quantity has to vanish identically. Okay. So it's not like you kind of look for a configuration for which this is zero, and then in some other situation it is not equal to zero. That's not the case, because the right hand side is identically zero, so this expression has to just vanish. Period. Okay. Now we know that there exists a similar equation that we had derived using the Bianchi identity. Okay. Now, in fact, what I want to say before that is that, like, if you have some expression which vanish identically, then it typically smells of a Bianchi identity. Okay. So, like, for example, in electromagnetism, you may have to show that del dot E is equal to zero or del dot E is not equal to zero by depending upon what is the charge distribution. If there is no charge in the space time, then del dot E would just be zero. Okay, but you need to show that. Okay, on the other hand, del dot B is equal to zero is not something you need to show, because that just directly follows from Bianchi identity. That it has to be identically kind of satisfied. Okay, it has to be. I mean, there's nothing that you need to do to kind of show that. In fact, if you want to show that del dot B is not equal to zero, you'll have to do some work actually. Okay, that you need to postulate some new kind of particles saying that they could source the magnetic field and stuff like that. Okay, but del dot B equals zero just directly follows from Bianchi identity. So similarly here, that this should be satisfied automatically kind of gives you a feeling that it must be coming from some Bianchi identity. Okay, so we have already studied the Bianchi identity and an equation that follows from the Bianchi identity, namely G alpha beta D alpha acting on too many alphas. Okay, I should have written down something else, maybe gamma. Okay, but the main point is that, like, that this equation was shown to be zero. Okay, and because of that, we figure out that in this equation, this would be identically true if B is minus half times A. Okay, so it tells you that the ratio of A is to B is 1 is to minus half. Okay, so which essentially means that you can pull A out and you can write down this equation to be R alpha beta minus half times G alpha beta R is equal to T alpha beta. Okay, so that is the condition which comes from the fact that T alpha beta has to be covariantly conserved. Okay, now what remains is to figure out what this A is. Okay, so to determine A, we again kind of go back to the non-relativistic limit, and in the non-relativistic limit, we find that that our equation was Laplacian acting on the gravitational potential was equal to 4 pi times the Newton's constant times the mass density. Okay, so on the other hand, phi in the relativistic formulation was given by was sitting inside G00, and that relation was minus 1 times minus 2 pi. So let me just go back and show it to you again. Okay, so here's the thing. Okay, so what we'll do is we'll try to bring the Newton's equation in this form. Okay, minus 1 has no role to play because there are two derivatives acting on it, but you can convert this equation by multiplying by minus 2 on both sides and replace minus 2 phi by G00. Okay, that gives you minus 8 pi Gn sitting around here. Okay, and you could therefore say that A, the constant that we had not determined, is just minus 1 over 8 pi Gn, because A is a quantity which is sitting actually on the left hand side of our equation. Right hand side was just T alpha beta. Okay, so this kind of limit to non-relativistic equation gives the guidance in figuring out what this constant is. Okay, so let's put that back in, and that gives us the equation, which is R alpha beta minus half G alpha beta R disaster. Okay, that's it. There are some other
Sir,
errors. Yes, please.
so originally was this derived using this Einstein-Hilbert action or
Yes,
by?
we will do that also. But Einstein-Hilbert action came later actually. Einstein derived the equation uh, by this analogy, in fact. Okay. Uh, Einstein-Hilbert action is not there in the original paper. It is there in the later paper. In fact, after the Einstein equation, Hilbert proposed that this equation actually should come from some action principle, and he proposed the action. Okay, so in fact, for quite some time, people continued referring to that as only Hilbert action. Only physicists call it Einstein-Hilbert. Mm. So yeah, so this is more like historically, this is the path that was followed. Okay, maybe I should not go back trying to correct this equation. I forgot where there was a correction, but it doesn't matter right now.
It was in the equation,
Yeah,
Einstein
it was in
equation.
yeah, it was in some equation, but like I'll do that later, I think. Yeah, this alpha was common. I'll handle it later. But I think this is more serious error, so I think I should correct that first. Okay, so what you get is the equation which is r alpha beta minus half times g alpha beta times r is equal to minus 8 pi gn times t alpha beta. So there is r back in its place. Okay, and so let's first check again that we managed to recover the Newton's equation. Now this may look like a kind of circular argument, but nevertheless it is still worth checking that, like, after putting this uh, parameter alpha to a to b minus 1 over 8 by gn, that everything works out correctly. Okay, so of course, to do that we need to do multiple approximations. So first thing that we do is to assume that we are working in a static weak field approximation. Okay, so that means the metric is almost Minkowski like metric. Okay, with small fluctuation around that or small deviation from the Minkowski metric. Okay, so so to do that, let's kind of understand each word that is mentioned out here. Okay, so let's try to understand what is the meaning of static limit. Okay, so typically when you look at a solution to Einstein equation, uh, it would have kind of metric written in terms of all space-time coordinates, and that means g alpha beta as a function of x. Okay, and if it is a function of all space-time coordinates, then of course it will also be a function of time because it's part of the x mu. Okay, so when we want to look for a static solution, okay, we'll have to impose certain conditions on what is the form of the solution. Okay, so before we talk about static, let's talk about something called a stationary solution. Okay, so when we say a solution is stationary, by that we mean that the metric components have no explicit dependence on time. That means you write down g alpha beta as a function of only xi and not x0. Okay, g alpha beta, no matter what is the value of alpha beta, g alpha beta is function of only spatial coordinate and not time coordinate. Okay, now simply because it is not dependent on time does not mean that it doesn't evolve in time actually, but it I mean it has no explicit time dependence. Okay, so that is what one means by a solution being stationary. Okay, now so just to kind of give an analogy, as I was mentioning that like many times the gravitational setup has good hydrodynamic descriptions. So here's the hydrodynamic analogy. That suppose you are looking at steady flow of a fluid, okay, then you are basically, so suppose you are looking at a river, water is flowing, but you are looking at a particular point in the river, okay, and at a particular point in the river, you are not following a particular liquid drop inside the river, but you are looking at particular point, spatial point in the river. So at every instant of time, there is a different liquid drop, water drop, which is crossing that point, right? So what you're saying is that like no matter which water drop is crossing at that point at any given time, okay, the velocity of that at that point is fixed. Okay, fine. That velocity is not changing with time at that particular location. Okay, so if you go to some other point, the velocity would be different. Okay, but at that point, no matter which water droplet is crossing, all of them would have the same velocity, and it is independent of time. So the stationary metric is of that kind, that there is no explicit dependence on time. Okay, and therefore if you look at the system at a particular point, you would find that a particle would have a fixed velocity or fixed acceleration at that point. If you look at some other point, it would have a different velocity and different acceleration. Okay, and therefore a different, effectively different time dependence. Okay, so that is what we mean by metric being stationary. Okay, now metric being stationary does not, remember, like there are two places where the time components get in. One place is where, think of metric as functions of space-time coordinates, and you say that the metric is not a function of time coordinate. Okay, that is one thing that you could do. The other thing that you could do is to say that that you have a metric which is written whose components of alpha beta, and alpha beta take values which are like only say ij. Okay, and alpha beta take value only 0 0, but they do not take value which is like alpha is 0 and beta is I, something like that. Okay, so when you are looking at a stationary solution, we are not imposing any of these conditions. You may have Gij non-trivial, you may have G00 non-trivial, and you may also have G0I non-trivial. Okay, so stationary solution does not impose this condition on what are the values of the metric components which are non-vanishing. Okay, fine. So stationary solution therefore tells you that if you take a partial derivative of G alpha beta with respect to time, that vanishes. Okay, fine. But you may have, as I was just saying, you may have G0I component non-vanishing. Okay.
So,
yes.
So when we talk about Einstein equation, its solutions are the metric, right?
Yes.
So what makes us say that a priori that okay, that metric would be time independent, explicitly time independent?
Well, nothing actually. Nothing tells you that that metric could be time independent. Okay. In fact, as we will see that there is no guidance on what kind of solutions you would get by just looking at the equation. Okay. So only guidance that we will use is some kind of symmetry principle. Okay.
Okay.
But all I'm trying to do right now is just giving you definitions. That something is called a stationary solution. Okay. Then stationary solution is defined to be this. Okay. I'm allowed to define whatever I want. I may not get a solution which is consistent with my definition, which is also fine. Okay. But if I find a solution which is consistent with this definition, then that solution I will call stationary solution. Right?
Okay.
Okay, so these are just definitions right now. I am making no claim about what kind of solution we will land up with. Okay.
Fine, sir.
Fine. Okay, so let's now look at the next step, and that is called the static solution. So static solution, of course, is a solution which is stationary. That means the metric components don't have explicit time dependence. Okay, but it's also in addition time reversal invariant. Okay, now you look at G0I. If G0I is a component that you are looking at, then that is multiplied by dx0 dxi. If you consider time reversal transformation as a symmetry, then dx0 will go to minus dx0. And if you want to have your metric to be invariant, then that tells you that G0I should go to minus G0I. And G0I is equal to minus G0I tells you that G0I should be equal to 0. Okay. So therefore, when you go to static solution, that means you not only impose the condition that G alpha beta is independent of time, but you also impose a condition that G0I is equal to 0. Okay. So that is the kind of configuration that we are looking at. Okay. So
I didn't get it.
Okay. So let me repeat again. So you have understood what is a stationary solution, right?
Yes, sir.
So stationary solution is precisely defined by this equation that any metric component is independent of time. You take time derivative, it just vanishes. Okay. Now, this does not tell you anything about what values alpha beta can take. It can be G00, G0I, Gij, anything is allowed. Okay. Fine. All of them have only one property, that if you take its time, their time derivatives, they vanish. Okay. So you may have G0I non-zero, which is maybe just constant, or it may be just a function of spatial coordinates, but not function of time coordinates. That will satisfy this condition. Okay. Now, what we want to do is to define a static solution, and static solution, again, this is a definition. Static solution is defined as a solution which is stationary. That means it satisfies this condition. And in addition to that, it is time reversal invariant. Okay. Now, what I was saying was G0I, when you write down a line element, d tau squared is equal to G alpha beta dx alpha dx beta, then G alpha beta dx alpha dx beta contains a term which is G0I dx0 dxi. Okay. Is that okay?
Yes, sir.
Yeah. So now if you do a time reversal transformation, then dx0 goes to minus dx0. Okay. And you want to say that your solution is invariant under time reversal transformation, means d tau squared is not affected by this transformation. So if that can only happen if G0I goes to minus G0I, such that G0I flips sign, dx0 flips sign, such that G0I dx0 dxi does not change sign. Okay.
Okay. I mean, it's slightly, the nomenclature is slightly confusing. Static and stationary usually mean the same thing, but
no, not at all. Not at all. I mean, okay. Okay. I mean, I'm not talking about English. I'm talking about the definition out here, and
yeah. Now I got it.
Yeah. So this is not a literature class, no, unfortunately. It is a class on general relativity, and we have used these words to define something. Okay.
I was talking about classical mechanics. Anyway,
no, not even in classical mechanics. Even in classical mechanics, stationary is different from static. They are not same.
Okay.
In fact, in physics, stationary and static are different quantities. Whether you do non-relativistic mechanics, relativistic mechanics, or general relativity. Okay, they are different.
So,
yes.
Shouldn't we make some sort of a coordinate independent statement for stationary, like some
No. Because you can bring a metric which is static, by doing a coordinate transformation, and it will not look static at all.
Yeah, okay. But then we'll have to say things like, suppose in a universe where we have some stationary metric, for some observers it won't look stationary.
Yeah, obviously, no.
Like
a moving observer may not see that object to be stationary, right?
No, but the universe itself, like the cosmological things will be different for them.
Of course, they are different. No, there's nothing. I mean, that is why it's called relativity, no. Otherwise, it would have been called general absolute. This is general relativity. It is relative with respect to observers, right? It's like even in black hole physics, infalling observer sees a different kind of metric, which is not static at all. Whereas black hole, say, Schwarzschild metric is actually static, right?
Okay.
So in fact, we will write down a variety of metrics for Schwarzschild black hole. Not all of them are looking static. Okay, but that is different frame. Infalling observers is. Sorry.
Your voice is cutting a lot.
Oh, my voice is cutting again. Oh boy. Yeah. Now
Yeah,
it's
now
telling
it's
me
fine.
my, yeah. The voice becomes fine when it tells me that the internet is unstable actually. Yes. Okay, now you can hear me, right?
Yes, sir.
Okay. So what I was saying is that like even in the black hole physics, whatever metric that asymptotic observer sees is not the metric that infalling observer sees, or not is not the metric that the outgoing observer sees. You know, they are different, and so therefore there is no invariant statement about what's called, I mean, coordinate invariant statement of what is called stationary versus static. Okay, but what I'm trying to say is that like if you obtain a particular solution in a particular form, okay, you should be able to classify them as stationary versus static in a particular coordinate system. Okay, anybody who is kind of badly accelerated with respect to a static coordinate system may see a metric which is quite different. Okay, that's fine.
So
Okay, yeah, sure.
like on the same regard, like if the universe is expanding,
Yes,
that is a coordinate invariant statement.
that is right.
Then why should we not like make these, like we should be making these statements in some covariant terms, equation wise. Like if the universe is stationary, it should be stationary for everyone, right?
Yeah, no, 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 no. See, expanding universe is nothing to do with it being stationary, no?
Yeah, it's opposite, but I'm just saying
Yeah,
some like physics is the same for everyone.
that is right.
If the
So,
universe is expanding, but it should be like the rate of expansion might be different because the coordinates are different, but
yeah,
the actual notion that the universe is expanding should be the same.
that is right. But if you look at the co-moving observer, okay, the co-moving observer doesn't even see the expansion in its own coordinate system, right? It feels that its coordinate system is actually static, right? Okay, so only when you kind of make observations of other objects which are either receding away from you, you are coming closer to you, that you decide whether the universe is expanding or contracting, right?
Yeah.
Yeah. So within a given patch, there is, I mean, like it's like so suppose you can look at, say, I mean, since you have done the course, suppose you look at Friedman-Robertson-Walker metric, okay, then the the scale factor of the metric is just the overall factor sitting outside, right? You can do a coordinate transformation such that dt squared and dxi squared, everything sits inside and a factor sits outside. Okay. So with respect to that overall scale factor, the metric seen by the observer is totally static actually, right? So what it is telling you is that like in some sense, if the objects were not moving, uh, not having their own velocity, it's like, Earth goes around the sun. Okay, but imagine that like, Earth was not going around the sun. Okay, or some stars were not rotating inside the galaxy. You know? And if you just kind of were taking a static structure of that kind, and if you wait long enough, the objects would have still receded from each other simply because the fabric of the space-time is kind of growing in size, right? It's like write down a fixed metric and then just you say that like, okay, yesterday the lengths were measured in centimeters. Today I'm measuring length, or yesterday the lengths were measured in inches. Today I'm measuring them in centimeters, and therefore suddenly all these distances which were 1 inch long, I have suddenly, I mean, in the units of inch they were 1 unit distance away. Now they have suddenly become 2.5 unit distance away. Okay, that's the kind of stuff that is happening actually. Now, of course, we don't have everything sitting around doing nothing. All the objects are having are moving, going around something or other. Okay, but in the cosmological picture, this motion of stars or planets or galaxies is not so important. You really are looking at expansion where you are looking at clusters of galaxies going away from clusters of galaxies, really. At the largest scale that the expansion is being seen, really. Okay. So if you look at any, any patch roughly, say of the order of, say, the size of the Milky Way, you don't really see any expansion. You see the whole thing as a static patch. In fact, like, you can add Andromeda also, galaxy also, which is the nearest one. And in fact, you find that Andromeda galaxy is coming closer to us, in fact, and not going away from us. So there's no expansion within the small cluster of few galaxies in the neighborhood. Okay, so cosmology has to be understood within that perspective, that in the largest possible scales, that there is a homogeneity and there is isotropy and there is a uniform expansion. And in fact, now what we see is uniform accelerated expansion, actually. Okay. Am I connected?
Yes.
Hello? Oh, yeah. Okay, thanks. Okay, so coming back to the static thing, therefore, what we do is that we, of course, impose the stationary condition, and we also impose that the off-diagonal component of the metric vanishes. That means you can write down your metric as d tau squared is equal to g00 dx0 dx0 plus gij dxi dxj. Okay, but there is no cross component between time and space. Okay, now, as I said, that this is not a coordinate independent statement. You can always do a coordinate transformation, and these conditions are not valid. Okay, fine. In fact, stationary solution condition also is not valid, simply because if the object is moving and that moving object's frame, what I call a stationary metric is not stationary metric. Okay, just a coordinate transformation which is time dependent. Okay, fine. But the purpose of defining this is that, like, if you look at a weak field limit, then by weak field limit, we really mean that G alpha beta is a small variation from the Minkowski metric. So G alpha beta is not exactly eta alpha beta, but eta alpha beta plus some epsilon times something like H alpha beta. Okay, and that is the quantity that we are interested in as to what H alpha beta is telling us. Okay. Now, in addition to that, we also have to take non-relativistic limit, because Newton's equations are non-relativistic equations for gravity. Okay, and we are familiar with how we take non-relativistic limit. We say that the time component of the line element is much bigger than the spatial component of the line element. Okay, this just corresponds to saying that CDT is larger than dx. Okay, velocities are small. Okay, so yeah, so this statement is same as this statement, really, that you claim that the velocities are small. Okay, so now if you want to take this limit, it is kind of convenient to write down Einstein equation in a little different form, and that form is typically is referred to as what is called the trace reverse form. Okay, so we'll just go through that trace reverse formulation. It is just convenience. You don't have to do this. You can work with the original Einstein equation also. Okay, so trace reverse form just corresponds to the statement that you write down Einstein equation and take a trace of it. That means you contract these indices. That just means you multiply by G alpha beta. I could have written minus 8 by Gn in the denominator here, but I just chose to just write A instead. Okay, so when you take a trace on both sides, then of course on the right hand side you get the trace of energy momentum tensor, which I am going to call T. Okay, and on the left hand side, G alpha beta R alpha beta gives you Ricci scalar. That is how the Ricci scalar was defined. Okay, whereas G alpha beta would give you a number. Okay, and that number depends on how many dimensions in which you are studying this problem. Okay, now we are of course studying it in 4 dimensions. So G alpha beta is just going to be 4 for us. Okay, so that makes this number -2. So you get R minus 2R. Okay, that is what you will get. Okay, so you get the equation A times R minus 2R is equal to T. Okay, it just tells you that A times R is equal to minus T. Okay, just one step from here. Okay, fine. So what we could do now is that we can replace this Ricci scalar by the trace of energy momentum tensor. Okay, and take that expression and pull it on the right hand side. Okay, so we get an expression which looks like this, that A times R is replaced by minus T. Okay, then G alpha beta times minus T is pulled on the other side, and you get A times R alpha beta is equal to T alpha minus half G alpha beta T. Okay, so instead of writing it in terms of Ricci scalar, we are writing it in terms of the trace of energy momentum tensor. Okay, many times you will find that this may be a more convenient form of the equation for doing certain calculations than actually work with the original Einstein equation. Okay, fine. Okay, so of course now we want to take the non-relativistic limit, and in the non-relativistic limit we have energy which is much greater than the momenta. That means rest mass is the dominant contribution to the energy than the kinetic term, and in that case T00 is the most dominant piece inside the energy momentum tensor. Okay, and if you're looking at that, then the trace of the energy momentum tensor therefore has a most dominant contribution coming from T00 times G00, right? Because you need to contract these indices, and contraction can happen only with one upper index and one lower index. Okay, but G00 to leading order, remember G00 was -1, -2 pi with downstairs indices. G00 upstairs would be again start with -1, but the factor would become +2 pi. Okay, but that 2 pi is a next order correction, so we will ignore that. And so therefore to leading order G00 T00 is just minus T00. Okay, so we can just put that back up here. Okay, we are looking at R00 is equal to T00 minus half times G00 times T. Okay, but T itself is T00 again with a minus sign. Okay, so you can kind of manipulate that expression to get half T00. Okay, there are too many minus signs here. T itself is minus T00. G00 is also -1. So those two minus signs cancel and this minus sign stays, and that gives you half. Okay, and in this limit, of course, the T00 is proportional to the mass density. Okay, now of course it is mass density plus the kinetic term of the for the mass distribution, but in the Newtonian limit it makes sense to kind of ignore the kinetic term, because in the Newtonian limit you actually consider the static mass distribution generating the gravitational potential. Okay, so the mass distribution actually did not have any kinetic term. Okay, so let's kind of do the same thing. In the static weak field limit, G alpha beta has a dominant contribution coming from G00. G I J are down by V squared by C squared factor. Okay, and there is no G0I because we are in the static limit. Okay, so there is a term which is of order 1, then there is no term of order V by C, and the next non-vanishing term is directly at order V squared by C squared. Okay, and if V is reasonably small to leading order, you can just ignore that. Okay, so G alpha beta reduces to this, and let's write that as -1 plus H00. Okay, so that is a kind of deviation from the Minkowski metric. Okay, R00, which is the 00 component of the Ricci tensor, is should have inequality. Okay. Okay. So that is written in terms of the Riemann tensor in this particular fashion, and you can write that in terms of the Riemann-Christoffel connection as an expression like this. Okay, all I've done is basically kind of use the Riemann tensor definition and just written in terms of Riemann-Christoffel connection. Okay, now so what we'll do is that we can simplify our life by working in a frame in which the we will work in a frame in which gamma is 0, but derivative of gamma is not. Okay. In that case, computing Riemann tensor is quite easy because the last two terms just vanish, and we really need to look at only first two terms. Okay. So so that's what we will do. But among these first two terms also, the first term is of no consequence simply because we are working in static limit, and therefore time derivative of any component of metric would just vanish. Okay. So our R00 therefore just reduces to minus del I of gamma I00. Okay. Now just substitute the definition of gamma I00, which is half times Gij times del 0 of G0J plus del 0 of J0 minus del J of G00. Okay. We are in the static limit, so G0J is just 0. Okay, so therefore these two terms also vanish trivially even without taking time derivative, and but even if this was non-zero with time derivative they would have vanished anyway. Okay, so what you land up with is an expression like this. Okay, and that gives you a del squared of the H00. Okay, because G00 and H00 differ by a constant, so when you take derivative, it doesn't really matter. Okay, so it gives you answer minus, it gives answer half times the Laplacian acting on H00. Okay, fine. So now remember that G00 is defined as -1 -2 phi. So H00 is really -2 phi. Okay, so therefore what you get is R00 is minus Laplacian of phi. Okay. So if you substitute that back into this expression, you precisely get Laplacian on phi is equal to 4 pi Gn times rho. Okay. So this may seem like a circular argument, but as you can clearly see that you need to make multiple assumptions, like you're looking at static and weak field limit of the equation of the fields to actually arrive at this solution. Whereas the earlier derivation of A being minus 1 over 8 pi Gn and all are really done by using the analogy of the relativistic equation with the non-relativistic equation. So in that sense, it is satisfying to get this equation back by taking appropriate limit. Okay, any questions?
Sir, I have heard that simplest generalization of this equation, like let's say Laplacian changing by something like box, that does not explain gravitational lensing.
That does not explain gravitational lensing.
Yeah. I mean, I don't know, but how does it happen? I mean, naively one would have thought that Laplacian changing like something like box and...
Yeah, but well, the box has to be defined in a correct fashion, right? I mean, see, gravitational lensing is actually related to what is called the bending of light, right?
Yeah, yeah.
So in that case, what you are actually looking at is the trajectory of a particle, okay, due to a gravitational source, right? Okay. What we are doing here is actually determining the gravitational potential due to a stationary. Oops. Can you hear me? Hello?
Yes, sir.
Okay, I seem to, the stability of internet is more problematic actually. Okay, so what I was saying was that like that is a situation where you have a test particle which is moving in a gravitational field created by some quote unquote stationary object, right? Whereas what we are doing here is a gravitational field created by a stationary object, and that is all. We are not trying to solve anything in the background of the gravitational potential. Okay, so this equation is not good enough for you to tell about bending of light or for gravitational lensing. You need more information. You need a probe particles to be determined. Okay.
Okay, sir.
Okay. Fine. Okay, so let's kind of get back to our equation. This is R alpha beta minus half G alpha beta R is equal to T alpha beta. Okay, and given that it is symmetric in alpha beta and alpha beta take 4 values, it is given a symmetric tensor would have 4 into 5 by 2, which is equal to 10. Okay, so there are 10 equations out here. R alpha beta minus half G alpha beta R is equal to something T alpha beta say. So there are 10 components in the Einstein equation, and it is just as well because G alpha beta is also a symmetric metric, and therefore it also has 10 independent components. Okay, so it seems like a good thing that you have 10 equations and you need to determine the 10 components of the metric. Okay, but what happens is that that Einstein equation actually has to satisfy this Bianchi identity, and this of course is true identically. Okay, and there's a contraction between alpha index here, but beta index is free, so therefore there are 4 such constraints. Okay, so these 4 constraints basically tell you that it is not that you have 10 independent equations, but you really have 6 independent equations. Okay, now we seem to be in trouble because we don't seem to have a sufficient number of equations to determine 10 components of G alpha beta. Okay, but that's not quite true because G alpha beta also has some additional conditions, and that is the following: that if G alpha beta is a solution to the equation of motion, then a new solution, the new metric G prime in the new coordinate system X prime, which is related to the original coordinate system X by some coordinate transformation. Okay, this new G prime is also a solution to equation of motion. Okay, so therefore, not only that this G alpha beta is a solution, but anything which is generated from it by general coordinate transformation is also a solution. Okay, so that requires you to write down 4 functions like this. Okay, and these 4 functions kind of tell you how these 10 functions are related to these 10 functions. Okay, so effectively only 6 are independent out here also, because 4 of them can be just fixed by these doing coordinate transformations. Okay, so effectively you could say that that 4 components of G alpha beta are quote unquote unphysical. Okay, and therefore you have 6 effective components here and 6 effective equations in the Einstein equation. Okay, so we are still seem to be in good shape. Okay, well, this is only a counting of these quantities. In reality, nothing is in good shape at all. So let's take kind of a mathematician's hat here and say that okay, Einstein equation is just a coupled partial differential equation. Okay, there are just 10 equations, all kinds of components are written out there, and they are all coupled equations. Okay, what is the status of this? Okay, so the first thing is that it is very complicated for various reasons. And first thing is that it of course contains derivatives of the Riemann-Christopher connection and the products of Riemann-Christopher connection. Okay, so what we actually remember, Riemann-Christopher connection involves inverse metric as well as derivative of metric. Okay, so therefore if you have the equation which contains products of Riemann-Christopher connections or derivatives of Riemann-Christopher connections, then you not only have derivatives of the metric, but you also have derivatives of inverse of metric. Okay, so imagine you write down say Klein-Gordon equation, which is box phi is equal to something. Okay, say m squared phi. Okay, But imagine somebody says that like, okay, you not only have phi, but you also have phi inverse. So you have equation something like box phi plus phi squared times box of phi inverse. Okay, that kind of stuff is equal to m squared phi squared plus m squared phi inverse. Okay, or something like that. Okay, then of course the equation starts looking complicated because there is a cubic term sitting around. There is a derivative acting on phi inverse, and the whole setup would start looking very complicated. Okay, now we don't do anything like this when we write down field equations, whether you are doing quantum field theory or whether you are doing classical field theory or classical mechanics, for example. But in case of general relativity, it is not that you have a choice. You know? Your Riemann crystal connection has G alpha beta and G alpha beta inverse. Okay, and therefore you are forced to have an equation involving both the field variable G alpha beta and its inverse and their derivatives. Okay, so that is one thing which already makes the equation quite complicated. Okay, now of course, because it involves products of Riemann crystal connections, and also Riemann crystal connection involves metric and its inverse, makes the equation badly nonlinear. Okay, and because the equation is nonlinear, if you obtain one solution, say G alpha beta, or rather if you obtain two solutions, G alpha beta and G tilde alpha beta, it doesn't mean that A times G alpha beta plus B times G tilde alpha beta is also a solution. Okay, so say in quantum mechanics, Schrodinger equation is linear. The Dirac equation is linear. Okay, so therefore, if you obtain two different solutions, superposition or linear combination is also a solution. Superposition principle is a very kind of central thing in quantum mechanics, but clearly it is not. I mean, it does not have any position out here, simply because if you try to superpose or if you try to take linear combination of two solutions, it is most generally is not a solution. Okay, so that makes the system kind of more complicated. Knowing different solution does not mean you have kind of parametric formulation of new class of solutions. Okay, fine. Now you may say that like, okay, let's try to simplify the system. Just set T alpha beta equals 0. Okay, if you set T alpha beta equals 0, then you can check by in a trace reversed form. That would just mean R alpha beta is equal to 0. Okay, because here is a trace reversed equation, or maybe let me just go up. This is a trace reversed equation. Okay, if T alpha beta is 0, then of course T is 0, and therefore R alpha beta is 0 automatically. Okay, so that seems like a simpler equation. Okay, but it is actually not. Okay, because these facts that derivatives act on inverse metric and non-linearities, we still have all of that sitting around in R alpha beta expression anyway. Okay, so the non-linearity has not been simplified by just taking away all the matter or all the sources in the equation. Okay, so even pure homogeneous non-linear equation is already complicated. Having non-homogeneous piece like external sources makes the problem even harder, but that's the status. Okay, so therefore to solve this equation, you typically need to make simplifying assumptions. Okay, and typical simplifying assumption is to assume that the solution has high degree of symmetry. Okay, so in spite of all negative things that I have said on this slide, we have been able to solve Einstein equation in many cases. We know large number of solutions to Einstein equation in the absence of sources as well as in the presence of sources. So it's not like so this almost gives a bad publicity to the equation, but in reality we have managed to obtain a large class of solutions. Okay, many of them of course do enjoy a high degree of symmetry, but there exist also other techniques which are typically kind of go under the name of solution generating techniques, that you kind of trade off the Einstein equation to some other equation. You write down some other bunch of equations and say that any solution to this set of equations guarantees that you have solved the Einstein equation. And then in those set of equations, you find one solution, and then starting from that solution, you find a bunch of solutions through a technique called solution generating technique. And then for each such solution, you are guaranteed that the Einstein equation is satisfied. And that is one way of generating large classes of solutions. Okay, we will not get into that. It's a bit advanced topic, but just to say that, like, in spite of all these complications from a partial differential equation point of view, it's not that like we have not been able to find any solution. We do have large class of solutions to this equation. Okay, fine. So here's the thing. Somebody wished to get Einstein equation from the action principle. So let's try to fulfill that wish. Okay. So so let's first try to derive Einstein equation, or let's try to derive the vacuum Einstein equation first. Okay. So so let's consider the Einstein action, and so this is where am I? Yeah. So it's the Hilbert-Einstein action, which is integral d4x root of minus the determinant of g times the Ricci scalar. Okay, and we want to kind of use this action to derive the vacuum Einstein equation. Okay, so of course, to derive an equation of motion from action, you usually you use the variational principle. So you claim that excuse me. So you claim that that you change the dynamical variable. In this case, the dynamical variable is metric. So you say that you change the dynamical variable a little bit, and that generates some change in the action. You demand the stationarity condition. That means the first variation of the action vanishes, and that would give you the equation of motion. Okay, the usual thing that you would do in, say, Lagrangian mechanics, or even in quantum field theory, classical field theory, whatever. Okay, fine. So here's the action, and we are going to vary the inverse metric. Okay, the reason why we are going to vary inverse metric is because we want to get inverse metric as indices upstairs. Okay, so that variation will have the objects multiplying that variation, which will have downstairs covariant indices. Our equation is written in the covariant form. Okay, indices downstairs. Okay, nothing great about it. You could just pull those indices upstairs if you wish, but given that we have defined it in that fashion, it may be convenient to just vary the equation with respect to the variation in the inverse metric. Okay, so here is the variation. So small change in the action for small change in G alpha beta would be like this. It could vary. I'm writing the Ricci scalar as G alpha beta times R alpha beta, where R alpha beta is the Ricci tensor. So either it could vary the Ricci tensor, or it could vary the determinant, or it could vary the G alpha beta. Okay, so these are the three terms that you could have. Okay, is that fine?
Yes, sir.
Okay, so so among these three terms, we already see that the last term is proportional to variation of the inverse metric by itself. Okay, so we don't have to do anything with this term, because what we want to do is we want to ask what is delta S Hilbert by delta G alpha beta with alpha beta contravariant indices. Okay, so we can pull the delta G alpha beta down here. Okay, this piece is fine. Okay, we need to ask what we are going to do with these two pieces. Okay, so let's first look at the second term. Okay, so we need to manipulate both of them, but we'll look at the second term first. Okay, so to do that, let's just consider a matrix, any matrix M. Okay, and any matrix could be written as exponential of log of M. Okay, so as you can clearly see, we haven't done anything. Exponential of a log is just 1. Okay, so that's why M is equal to e to the log M. Okay, and similarly, if you use the same fact, you know that log of determinant of M is same as the trace of log of M. Okay, so we'll use these two conditions to.
So your voice is.
Hello, are we connected again?
Yeah,
Yes.
now.
Yeah. Okay, so let me share the screen again. I think this is yesterday also it happened at the same time, huh? Roughly around 12:10, 12:13. Okay, can you see the screen?
Yeah, we can.
Okay, great. Okay, so what I was saying was that we can write down any matrix as exponential of log of the same matrix. Okay, this is in some sense tautology, because exponential of log of any function is the function itself. Okay. Similarly, log of determinant of the matrix is same as the trace of log of the matrix. Okay. One way to do this is to actually just do a similarity transformation, which will diagonalize the matrix. Okay. And an arbitrary matrix cannot be diagonalized, but we are not interested in arbitrary matrices. We are interested in matrices which are symmetric. So, of course, we should be able to diagonalize them. Okay. So, and if you do the similarity transformation, then you know that it doesn't affect either the determinant or the trace. Okay, but when you take the log of that, then S, M, S inverse, S and S inverse log pieces will just cancel each other, and therefore diagonal piece will tell you that the term is proportional to the trace of log of M. Okay, so this kind of is a simple manipulation. Okay. Fine. So what we are going to do is to utilize this to determine the derivative or the variation of the determinant of M, because that is what we want to really do. Delta of root G. R is just sitting around here. Okay. The variation of R are the terms which is the first and the last term. Okay. We are just looking at variation of determinant, root determinant. Okay. So we'll use this fact that determinant M can be written as exponential of log of determinant M, exactly the same relation, okay, which is same as exponential of trace of log of M. Okay, if you take a square root of that, then it is just half the trace of log of M, because just take a square root of that quantity also. Okay, now here's a manipulation of finding out the variation of square root of determinant of M. Okay, so that corresponds to the function itself times. Okay, so you look at this expression, you vary this, corresponds to vary the exponential. But when you vary the exponential, you get exponential back plus the variation of the exponent, which is this term, half times delta of trace of log of M. Okay, fine. So now you can take the delta in and take the variation of log of M, which gives you M inverse times delta M. Okay. So you can look at this expression, and you could decide. I mean, what we really want in our case is variation of G inverse. So you can trade this off by saying that M inverse M is equal to 1. So therefore, M inverse delta M is same as minus delta M inverse M. Okay, so there is a minus sign out here. Okay, so here's a kind of way you would do a variation of square root of determinant. Okay. Now, of course, exponential of half of trace log M is again square root of M, determinant of M again. Okay, so you can put it back in if you wish. Okay. So let's apply this expression, this manipulation to variation of root determinant of G. Okay. So if you do that, then you get an expression which is delta root of determinant of G, which is root determinant G times half of G alpha beta times delta G alpha beta. Okay, which you can write using the last expression as delta of G inverse. Okay, you just trade it off by exchanging these indices. Okay, so what we will do is that we will kind of use this expression and do a bit of cheating to get our Einstein equation first. Okay, and then we will kind of try to justify whether that was cheating or not. Okay, so what we will do is the following. Okay, remember we have this equation. we have a variation of R alpha beta, variation of root determinant G, and variation of G alpha beta inverse. Okay. We said we don't need to do anything with this expression. We have just manipulated this expression, and we have to manipulate this expression. Okay. What I'm going to claim, okay, is that R, which is written as G alpha beta times R alpha beta, I interpret that breakup of Ricci scalar into G alpha beta times R alpha beta in the following way. I say that G alpha beta is of course the object that I want to vary, okay, but I treat R alpha beta to be an independent variable, okay. By that I mean that when I take a variation of S, I vary G alpha beta, but I don't vary R alpha beta, okay. So this is equivalent to saying that I am setting the term delta R alpha beta is equal to 0, because I am doing a variation of G alpha beta, and I claim that R alpha beta is an independent variable. Okay, so it doesn't vary. So I only need to look at only these two variations. Okay. So suppose you do that. Okay. Then delta R alpha beta will be set to 0, and you use this delta G alpha beta, which is given out here, plug it into this. The last term gives you delta G inverse alpha beta times R alpha beta. This gives you minus half times G alpha beta times root G. Okay. And you have to set this equal to 0. Okay. This is to be set to 0 for arbitrary variation of G alpha beta. Okay. And for the non singular metric. Okay. So therefore, if you write down this, you get Einstein, vacuum Einstein equation. Okay. So it's R alpha beta minus half G alpha beta times R is equal to 0. Okay. So so one can derive this equation by doing a cheat method, and as I said that it is a cheat method, so it is not a correct manipulation because G alpha beta and R alpha beta are not independent variables. But at least, are you with me with this derivation?
Yes, sir.
Yeah. Okay. So of course, as I said that like this is not the most kind of I mean, this is not the correct manipulation, but we will see that it's actually not wrong either. This manipulation is essentially going to be correct. Okay. By that I mean the following thing, that we actually should vary R alpha beta. So we should not set delta R alpha beta equal to 0. We should actually evaluate what it is. Okay. But that is not going to affect this result. Okay. That is the claim. Okay. So let's put this on a little more firm footing by actually studying the variation of R alpha beta. Okay. So to study variation of R alpha beta, let's begin with the Riemann tensor. Okay. So here's a Riemann tensor. This expression is something you should by now know because of course I have kind of manipulated, rearranged the indices. They are not alpha, beta, gamma, delta in the way they were defined earlier, because I want to get alpha, beta as a free index. So that's what the Ricci tensor has. So we just manipulated it a bit. But yeah, so you should know this formula by now. Let's look at the variation of the Riemann tensor. Okay, so that corresponds to variation of this gamma, or variation of this gamma, or variation of any one of these two. So either this gamma is varied, that is fixed, or this is fixed, sigma alpha delta is fixed, and gamma sigma beta is varying. Similarly, here sigma alpha beta varies. Okay, and in the second one you have a gamma sigma delta varying. Okay, so we have taken care of all variations. This. Okay, so totally 6 terms. Now, of course, as you can clearly see that to determine variation of the Riemann tensor, we need to figure out what is the variation of the Riemann-Christoffel connection. Okay, is that fine? So what we'll do is we'll not actually study the variation of Riemann-Christoffel connection by kind of writing that in terms of G and G inverse and stuff like that, because that is just longish manipulation. But notice some interesting relation which would help us write this expression in a simpler fashion. Okay, so suppose you do a variation of the connection, then what does that mean? That means you take the original connection, gamma, alpha, beta, gamma, and you replace that by gamma plus delta gamma. Okay, let's call that new connection gamma tilde. Okay, now remember that both gamma and gamma tilde are connections. Okay, so they transform inhomogeneously, but the inhomogeneous part of the transformation for both gamma and gamma tilde are same. Okay, so therefore, if you write down a quantity which is gamma tilde minus gamma, okay, suppose you write down a term which is gamma tilde minus gamma, then that is same as delta gamma. The inhomogeneous piece between gamma tilde and gamma will cancel, and therefore it tells us that delta gamma is actually a tensor. Okay. So therefore, although delta gamma is a difference between two non-tensors, okay, since those two non-tensors have the same inhomogeneous piece, the delta gamma happens to be a tensor. Okay, so what we'll do is we'll exploit this fact that delta gamma is a tensor. Okay, now remember we have delta gamma sitting around at various places. Okay, so we will kind of utilize the fact that delta gamma is a tensor and try to see whether this expression can be written in a more elegant form. Okay, now remember, if some quantity is a tensor, then let me just go back again. Now delta gamma is a tensor, definitely. Okay, but variation of Riemann tensor involves derivatives of delta gamma, and we know that derivative of a tensor is not a tensor. Okay, so what we want to do is to see whether we can kind of maintain tensorial nature of delta gamma, and that can be done by actually taking covariant derivative of delta gamma. Okay, so if you take a covariant derivative of delta gamma, then we are guaranteed that whatever new object you are going to get is a tensor. Okay, because that is the property of a covariant derivative. So here's a covariant derivative, d sigma acting on delta of gamma, alpha, beta, gamma. That is written out here. It has one countervariant and two covariant indices. That's why you have one plus sign and two minus sign. Okay, in this connection terms. Okay, so you can check that kind of expression makes sense. Okay, so what we'll do is that we will use this expression, okay, and find out what is the antisymmetric piece of this covariant derivative. Okay, so to do that, we antisymmetrize between sigma and beta. Okay, so if you do that, you have an expression like this: d sigma of delta gamma alpha beta gamma minus d beta of delta gamma alpha sigma gamma. Okay. So beta is and sigma are replaced, and there is a relative sign. Okay, so here are the terms. If you just look at them carefully, the first set of terms, these are these up to here. Okay, first four terms are precisely these terms. Okay, partial derivative with respect to sigma of alpha beta gamma, then gamma sigma rho gamma times delta gamma alpha beta rho, and so on. Okay, you can check this. So first four terms are exactly the terms which are written up there, and the last four terms, partial derivative acting on delta gamma plus three gamma gamma terms, are the terms where sigmas and betas are exchanged. Okay, that's what is this piece. Okay. Now, among these terms, you will notice that there exists one term, or rather two terms, which is the terms which involve sigma and beta on a gamma. Okay. So there is a gamma lambda sigma beta here and a lambda sigma beta here. Okay. They come with opposite sides. Of course, it's expected that they would come in opposite signs because they are anti-symmetrized with respect to sigma and beta on the left hand side. So they better vanish because gamma is symmetric in beta and sigma out here. So you better not have a term of that kind. So those terms just cancel out, and then you get expressions which involve 2 derivative terms and 4 kind of terms involving gamma and delta gamma. Okay, so here are the sorry. So okay, so now you can check, go back and just hold on. Okay, so now you can go back and check that this expression is same as the variation of the Riemann tensor. Okay, so what we find is, hello, I hope we are connected.
Yes, sir, we can hear you.
Yeah, so let me just kind of complete this argument because we are almost there. Some typo also. So what we find is that you can write down the variation of Riemann tensor as the kind of antisymmetrized covariant derivatives of the variations of Riemann-Christoffel connection, which are of course tensor quantities. Okay, so what you could do, this should have been subscripts actually, some error in this, so I'll correct that, but okay, I'll do that later. Okay, so now we can kind of contract these indices. We said beta is equal to gamma. If you do that, then you get R gamma alpha gamma sigma, okay, is equal to R alpha sigma. Okay, and therefore variation of R alpha sigma is just given by these terms where you contract beta and gamma. Okay, so here beta and gamma is contracted this way, here beta and gamma is contracted that way. You can see the 2 terms appearing this way. Okay, take this expression and put it back into our integral. Okay, so if you put that back into our integral, then we get an expression which is root g alpha beta, they come for a rise, delta r is this expression. Okay, replace sigma by beta inside this expression, you will get the terms which are like this. Okay, so you can check that is a beta derivative times delta gamma alpha gamma, gamma derivative of delta gamma, gamma alpha beta. Okay, and now what you could do is you can push this g alpha beta in, okay, into the equation. Use the fact that g alpha beta is covariantly constant, so therefore it can just go through the covariant derivative and multiply delta gamma. Okay, that manipulation allows you to pull this derivative, covariant derivative out and put this entire expression inside. Okay, if you do that, then you can show that this expression is actually a total derivative. Okay, it's a covariant derivative, of course, but with respect to this integration measure, this you can show that this is actually a total derivative. Okay, to put it a little differently, besides pushing g inside, if you had pushed root g also through the covariant derivative, then you can show that that covariant derivative just becomes ordinary partial derivative. Okay, so this entire expression can be written as a partial derivative with respect to x sigma of quantity which is root of determinant of minus g times this entire expression. Okay, these 2 statements are essentially equivalent. Covariant derivative with respect to this integration measure versus partial derivative with root g inside with respect to flat integration measure. Okay, are same statement. But given the fact that now this entire expression is a total derivative, it tells you that it has only a boundary contribution. Okay, it has no contribution anywhere else because total derivative of an integral of a total derivative only has a boundary contribution from the integral. Okay, fine. So therefore, you could say that this expression does not contribute to the equation of motion because it has only boundary contribution. One way to kind of say this is to say that if you look at variation, arbitrary variation of the metric, holding the kind of metric variation to be 0 at infinity, okay, then this term would not contribute. Okay, and as a result, we were in some sense correct to ignore this particular piece and kind of do a cheat way of getting the Einstein equation. Okay, now of course you would say that, like, okay, what if I look at a variation which does not vanish at infinity? Then of course you will have to worry about what is the boundary contribution. Okay, and the in that case the problem is little different because you have a boundary variation, and because you have boundary variation, your variational problem itself is not well defined. So for principle of variation to be well defined, you need to impose a specific, you need to add a boundary term to the action which will take care of the boundary variation of the Einstein Hilbert action. Okay, this is a very well defined subject. There are a lot of kind of boundary terms that have been written down. One of the famous one is what is called the Gibbons-Hawking boundary term, but there are various other kind of terms that you can write down. We will not get into that right now, but once you do that, once you add the so-called Gibbons-Hawking term, then your variational principle is well defined, and only then can you actually reliably get the equation of motion. What we are doing when we ignore delta r alpha beta was to say that all the variations vanish at infinity, and therefore there is no boundary contribution due to variation, and therefore we justify our cheat way of getting equation of motion by saying that delta r alpha beta is actually 0. Okay, and therefore this is Einstein equation. Okay, so I have already overshot this thing, but I think I'll stop at this point. Any questions?